So today we will study the Norton theorem. It is having few similarities and few dissimilarities with respect to the Thevenin theorem, which we have studied in the previous lecture. So what is the similarity? Let's consider that first. So similarity is that this theorem again simplifies the circuit to as per our needs. And next similarity is that the procedure of calculation of Norton resistance is same as that of the Thevenin resistance. Okay, two similarities. One, it simplifies the circuits. Second, it Thevenin resistance is equal to Norton resistance. The process is the same. Third similarity is that whenever we are required to verify the Norton's theorem, again it means that we have to calculate the current using the Norton's theorem and also verify that the current is flowing in the circuit is same if it is calculated with any other method. Okay, these were the similarities. Now we will consider the dissimilarities. Okay, so the dissimilarities are that in Thevenin theorem, our focus is on voltage source. Okay, voltage source, so that we calculate the effective Thevenin voltage in the circuit. Here in the Norton's theorem, our focus is on current source. Okay, in Thevenin theorem, our focus is on voltage source. Here our focus is on current source. One thing. Secondly, our Thevenin theorem simplifies the circuit in such a manner that the load resistance and Thevenin resistance are in series with the voltage source. Okay, but in the Norton's theorem, what happens? In Thevenin, it is based on the series combination of load resistance and the Thevenin resistance. Here, it focuses on the parallel combination of load resistance and Norton resistance. Okay, there was voltage source, here it is current source. There were in series, voltage source was in series with the load resistance and Thevenin resistance. Here now you can see in this circuit, here this is the last and the reduced form of the Norton's theorem. So what we get, the current source which is in parallel with the Norton resistance and the load resistance. Okay, again another dissimilarity is that Thevenin theorem focuses on open circuit principles and Norton theorem focuses on short circuit principles. Okay, you can see here it is written ISC, which is the short circuit current. Okay, which will act as the constant current source. Okay, so the similarities and dissimilarities are clear to you now. So consider this network which is given, and in this network there is a EMF or voltage source, and if that voltage source is having any internal resistance, then it is placed in series with that. But if it is not having any internal resistance, it is not placed. Okay, so this Norton theorem, it makes use of the fictitious constant current source. Okay, so it is not that that the circuit changes altogether and that voltage source is converted into the current source. It is the our assumption that it is changed into the current source because it behaves as a current source. Because the current, what current source does, the current source supplies the constant current irrespective of the magnitude of the resistance or the impedance. Okay, so here also the load resistance is supplied by the current, constant current. So we can say that the current circuit is converted into such a form that it behaves as a short circuit current is supplying the constant current to the load. That is why it is called the fictitious current source. Okay, so it makes use of the fictitious means phony, that unreal, that thing which is not present actually, but it is assumed. Okay, so it makes use of the fictitious constant current source in which the constant current delivered being equal to the current that would pass into the short circuit connected across the output terminals of the given network. Okay, so we will again focus word by word. Fictitious constant current source is clear. So it will, in which the constant current is being delivered. Okay, which is that current will pass through the short circuit of the output terminals of the network. Okay, so that means output terminals means the load resistance. So here is the short circuit current, or the same amount of the current is being flowing through the load terminals or the output terminals of any given network. Okay, so let's derive this parameters. So our focus is to calculate. Here three things are unknown to us, or you can say the known quantities are converted into three main parameters. First is the constant current source or the short circuit current. Second is the Norton resistance. Third is the Norton current. Okay, so let's go by the current example. So now let us focus on the circuit. So first of all, let me do the easy thing. Easy thing is that we have already studied the calculation and derivation of the Thevenin resistance. So its calculation is same. So focus on the middle circuit. Okay. So in this circuit, what you see, okay, what you can see that the EMF source is removed and it is replaced by its internal resistance, if any. Okay. Next is that load is removed and it is replaced by a open circuit. Only thing which is common between the Thevenin theorem and Norton resistance is that we open circuit the load and calculate the effective Thevenin resistance or Norton resistance. So here this small concept of the open circuit is there. Otherwise, we will be focusing on the short circuit current. Okay. So this circuit is open. So when the circuit is open, again we have to calculate the Norton resistance by calculating the current flow into the circuit. Okay, so current is assumed to flow from the node A towards the R3. So when it moves towards the R3, a node is there. So in this node, there is the current division taking place. So R1 and R is in this series, and this series combination is in parallel with the R2. Okay, and this combination is in series with the R3. Okay, is this point clear? It is just the repetition of what we have done in the Thevenin theorem. Now we will focus on the other thing. So I was telling you that what more we can do, we can use these brackets so that things are more clear to you. So here R2 plus R2 in parallel combination with R1 plus R is derived here, then it is added with the R to get the effective Norton resistance. Okay, so now let us focus on the other things. So as in the Thevenin theorem, we used to calculate the current which is flowing into the circuit. So same thing is done here as well. But what is the difference? The difference is that before calculating the current in the Thevenin theorem, we used to open circuit the resistance, load resistance. Here we will short circuit the load resistance. It is the difference. So now focus on the first circuit. So here EMF source is there and I1 current is flowing and the node comes, and in this node their current division will take place. So this I2 R3 is equal to I3 R2. Okay, now this is the same derivation. So this is the same which I have just derived you before the beginning this. Okay, so I2 R3 is equal to I3 R2. What change I have done, that maybe I should have assigned I2 current to R2 and I3 current to I3, but doesn't matter, you focus on the concept. Okay, so I2 R3 is equal to I3 R2, so R3 upon R2 becomes I3 upon I2, and if we add +1 to both the sides, so we can get the result that I1 upon I2 is equal to R3 plus R2. So I2 plus I3 is replaced by I1 according to the needs of the KCL. Okay, so now this I2 becomes I1 R2 upon R2 plus R3. Okay, so now the effective resistance is to be calculated. So now again be sure that this effective resistance is different from the Norton resistance. Okay, why it is different? Because in the Norton resistance, what we have calculated the current flow into the circuit from the load end. But now, since we are focusing on this circuit, so the current flow will be according to the EMF source. Okay, so the current flow will be from LHS to RHS. Earlier it was from RHS to LHS. So the net resistance of the circuit will be R1 plus R plus R2 is in parallel with R3. Okay, So see to it. So the current is flowing from LHS to RHS. It means that these R1 plus R is in series. Okay. And this R2 plus R3, R2 and R3 are in parallel. So the parallel combination of R2 and R3 is calculated, and then it is added with the series combination of R1 plus R to get the effective resistance of the circuit. Okay. So same thing we have done here, as I have shown. This R1 plus R is in series with the parallel combination of R2 and R3. So now we are available with effective resistance. EMF source is known to us. So I1 current is also known to us. Now it is just a Ohm's law type of situation. So V is equal to IR, EMF is known to us, effective resistance of the whole circuit is known to us. So we can calculate the current. Okay. So now since this I1 current is known to us, we can substitute this I1 current in this equation to get the I2. Why we are focused on I2? Because this is I2 is the same short circuit current which is flowing through the resistance. Okay. So that's why we are focusing on I2. Okay. So in this way we can calculate the I2. Rest is just the substitution part. You can see here that what we have done, we have, this is the I1. If we focus on the I2 equation, this I2 equation, this is the I1 current, which is, we are focusing on this. Okay. So this is the I1 current is substituted from this to this. Next, just this is just the calculation part. Now we have calculated the Rn as earlier. So now what was our requirement? Our requirement was to calculate the short circuit current and the uh, Norton resistance, so that the load current can be calculated. Okay. So now Rn is known to us, and short circuit current is also known to us. So we can apply this load current formula from the end circuit. Okay. Because what is in the last end circuit, there is the parallel combination of Rn and RL. Okay. So again, same thing that we have just derived. Same is, it is the repetition here, or you can do the KCL again and apply same. You can again do the this part, IN is equal to ILRL. If you do this, you will get the similar results. Okay. So now the short circuit current is available from ISC. We can substitute here. Rn is calculated from this circuit, calculated here. We can substitute here. So using these two substitutions, we will get the load current, or the current which is flowing into the load current. Okay. So is this clear to you?
Yes, sir.
Now we will, okay. So now we will go the definition part of the Norton's theorem, and we will take the numericals in the next class. So it states that the current in any passive circuit element RL in a network is same as would flow in it if it were connected in parallel with Rn and the parallel pair were supplied with the constant current ISC. Rn is the resistance measured looking back into the original circuit after RL has been disconnected and all the sources have been replaced by its internal resistance. ISC is the current which will flow in the short circuit placed at the terminals of the RL in the original circuit. Okay.